Hello friends, welcome to Active Abit Academy. In the last lecture we were discussing the problems on the moment of inertia. So in the last lecture we have discussed up to question number 5. So we will discuss question number 6 onwards in this particular lecture. So what is given in the question? Find the moment of inertia of a right circular cylinder about its axis. So in the first case we have to find the moment of inertia about the axis of the cylinder. In the second case we have to find the moment of inertia about a straight line through the center of gravity that is perpendicular to its axis. So in the first case we have to find the moment of inertia about the axis of the cylinder, and in the second case we have to find the moment of inertia about a straight line that is perpendicular to its axis, that is the axis is lying in the plane of the cross section. Okay, so let us draw this. So we have the cylinder like this. So we have a right circular cylinder. This is the cross section. Okay, so in the first case we have to find the moment of inertia about the axis that is passing through the center of gravity. So this is our axis. Okay, this is the axis of the cylinder. Axis of the cylinder, and the straight line that is perpendicular to its axis is this one. Okay, so this axis is perpendicular to the axis of the cylinder. So in the first case we have to find the moment of inertia. Let us take this as Iz and this is Ix. Okay, so in the first case we have to find the Iz. In the second case we have to find the Ix. Okay, so let us find this. Okay, so let us take an elemental strip of thickness dx at a distance of x from the x-axis. Okay, so this is our x-axis. Okay, so what is the elemental mass of this strip? This is our strip. So the elemental mass of this strip is, so basically it is a disk. If we see from here, this is a disk. Okay, this is a disk of radius a. This is a disk of radius a, and the thickness is dx. So what will be the elemental volume? So this is area into thickness. So elemental volume dV is equal to area, that is area of this disk into thickness. Okay, so we have dV is equal to area is pi a square into thickness is dx. This is our dV. So what will be the elemental mass? dm is equal to density times dV is equal to pi rho a square into dx. This is the elemental mass of this disk. Okay, so what will be the moment of inertia? So the moment of inertia of a disk that is about an axis that is perpendicular to its plane is given by, so suppose this is our disk. Okay, so we have the moment of inertia. Suppose we have a disk of radius a. So what will be the radius a and mass capital M? So a moment of inertia about an axis that is perpendicular to its plane is and passing through its center of gravity. This is center of gravity is given by m into a square upon 2. So in this case the mass is dm. So the mass of the elemental mass of this disk is dm. Okay, so the moment of inertia will be dm into radius square. The radius square is a. So dm into a square is the dm into a square upon 2. Okay, so dm into a square upon 2 is the moment of inertia of the disk. Okay, about an axis that is perpendicular to its plane and passing through center of gravity. So this we have discussed in the moment of inertia of the rigid bodies. Okay, so let us find this. So we have the moment of inertia as, this is our elemental mass. So we have the moment of inertia of this elemental disks. So we have di is equal to di is equal to dm into a square upon 2. So this is equal to a square by 2 into dm. dm is pi rho a square dx. This is our di. What will be the limit on this x? So x, this total height is h. So this is h by 2. This below the x-axis, and h by 2 height is above the x-axis. The value of x varying from, this is plus h by 2 and this is minus h by 2 and this is 0. So the value of x varies from plus h by 2 to minus h by 2. So we have this as minus h by 2. This is plus h by 2. Okay, so let us integrate this. So we have this as pi rho a4 upon 2 into x, and limit is from h by 2 and this is minus h by 2. So this is pi rho a4 upon 2 into h by 2 plus h by 2. This is h. This is pi rho a4 upon 2 into h. This is the moment of inertia of the cylinder. Let us place the value of rho. So we have the volume of this cylinder is, volume is equal to pi a square into h. This is area into height is the volume. So what will be the mass? Mass is equal to rho times the volume. So rho times pi a square h. Okay. So we have rho is equal to m upon pi a square into h. This is our density. So let us place the value of density. So this is equal to pi a4 h upon 2 into rho. The value of rho is m upon pi a square. Okay, so this will be equal to I is equal to m. This pi gets cancelled and this a square gets cancelled with a square. So we have this as ma square upon 2. This is the moment of inertia. So the moment of inertia about the axis of cylinder is given by ma square upon 2. So in the first case it is ma square upon 2. That is moment of inertia of a right circular cylinder about its axis is given by, this is its axis. Okay, and this is center of gravity. So this is ma square upon 2 is the moment of inertia of the right circular cylinder. Let us find the moment of inertia of a about a straight line that is perpendicular to the axis of the cylinder. How we can solve this? So let us revise the basics first. Okay. Let us consider an axis like this. Okay, so we have a disc lying in the plane of xy plane. This is x and this is y. Okay, so we have studied in the chapter of the moment of inertia of various rigid bodies, the moment of inertia of an axis that is passing through the center of gravity and perpendicular to the plane of the disc is given by ma square upon 2. What will be the moment of inertia about a straight line that is lying in the plane of the disc? Okay, that is lying in the plane of the disc and passing through the center of gravity. So this is ma square by 2. So let us consider by symmetry. This is perpendicular, both the axes are perpendicular. Let us take this as ix and this as iy. Okay, so let us take this by symmetry, both are same. So this is I and this is I. Let us take this as. So from the perpendicular axis theorem, we have ix plus iy is equal to I. So we have I plus I, sorry, this is equal to ma square by 2. This is iz, no? Iz. So we have ix plus iy is equal to iz. So we have I plus I is equal to ma square upon 2. So we have 2I is equal to ma square upon 2. So we have I is equal to ma square upon 4. So the moment of inertia about an straight line that is lying in the plane of this disc and that is passing through the center of gravity is given by ma square upon 4. Okay, similarly this is ma square upon 4. The sum of ma square and ma square upon 4 and ma square upon 4 both must be equal to ma square by 2 from the perpendicular axis theorem. Okay, so let us solve the second part of this chapter of the cylinder. Okay, so we have the cylinder like this. Cylinder like this. This is its axis. So we have to find the moment of inertia about this axis. Okay, this is Ix. Okay, so let us take an elemental disk, okay, at a distance of x from the x-axis. At a distance of x from the x-axis. This is our elemental disk, and the thickness of this is dx. Okay, what will be the elemental mass of this? So the elemental volume dV is equal to rho times of elemental volume will be area times of thickness. So area is pi a square into thickness is dx. What will be the elemental mass? Dm is equal to density times dV, rho dV. So this is equal to pi rho a square into dx. This is the elemental mass. Okay, so what will be the moment of inertia about an axis? So this is our elemental disk. This is our elemental disk. So what will be the moment of inertia about an axis that is lying in the plane of this elemental disk? Lying in the plane of this elemental disk. This is axis that is lying in the plane of the elemental disk. Dm, this will be equal to dm into a square upon 4. This is I dash. Okay, so from the parallel axis theorem, since this is I dash and this distance is x, so this is Ix. So we have Ix is equal to I dash plus this is dm into distance square. So dm into this is x square. Okay, so we have I dash is equal, Ix is equal to, we have this as dm into a square upon 4 plus dm into x square. Okay, so let us further simplify this. So we have Ix is equal to a square upon 4 plus x square into dm. So we have Ix is equal to a square upon 4 plus x square into value of dm is pi rho a square into dx. So we have this as pi rho a square into a square upon 4 plus x square into dx. Okay, so we have the limit from x limit is from minus h by 2 to plus h by 2, minus h by 2 to plus h by 2, because this height is h by 2 below the x-axis and h by 2 above the x-axis. So we have this varies from minus h by 2 to plus h by 2. Okay, so this will be equal to Ix is equal to, the value of Ix is pi rho a square, into, let us take this as 0 to h by 2 and take 2 outside. So this is 2 times of 0 to h by 2, and this is a square by 4 plus x square into dx. So we have Ix is equal to 2 pi rho a square into a square by 4 into x plus x cube by 3. Okay, so limit is from h by 2 to 0. Let us further simplify this. So we have Ix is equal to 2 pi rho a square into a square by 4 into h by 2 plus 1 by 3 into h by 2 ka whole cube. Okay, so we have Ix is equal to 2 pi rho a square into a square h upon 8 plus h cube upon 8 3 are 24. So we have this as Ix is equal to 2 pi into, let us place the value of rho. So rho we are having as density is equal to mass. So mass of this cylinder is m upon volume. The volume is area of cross section into height. So height is just area of cross section is pi a square into small h. Okay, so we have this as m upon pi a square into h into a square into, let us take h by 8 common. So h by 8 common, this is a square plus h square upon 3. Okay, so we have a square gets cancelled, h gets cancelled, and pi gets cancelled, this 4 gets cancelled. So we have Ix is equal to m upon 4, this is a square plus h cube, sorry, h square upon 3. Okay, so this is our answer of the second part. Okay, so in the first part we have ma square upon 2, that is about the axis of the cylinder. In the second case it is m upon 4 a square plus h square upon 3. Okay, so let us discuss question number 7. Okay, so how we can solve this? So we have a solid body of density rho is in the shape of a solid formed by the revolution of chordwide. Okay, so the equation of chordwide is r is equal to a1 plus cos theta about the initial line, so that the moment of inertia about a straight line through the pole perpendicular to the initial line is given by 352 upon 105 pi rho a5. Okay, how we can solve this? So let us solve this. So we have the equation of chordwide as r is equal to a1 plus cos theta. Okay, so let us have a plot of this. So we have theta versus, so we have the theta versus r. Okay, so when theta is equal to 0 degree, when theta is equal to 0 degree, we have this cos theta as 1, so this r value is 2a. When theta is equal to pi by 2, so we have cos theta 0, so this is a. When theta is equal to minus pi by 2, this is also 0, so this is a. When theta is equal to pi, and theta is equal to pi, the value of r is 0. So when we vary theta from 0 to pi, the value of r decreases from 2a to 0. Okay, so what will be the plot of this? So let us have the plot like this. So okay, so when we have the value of theta is 0, so this is the initial line, theta is equal to 0, this is theta is equal to pi by 2, this is theta is equal to pi, and this is theta is equal to minus pi by 2. So when theta is equal to 0 degree, we have the value of r as 2a, this is 2a. When theta is equal to pi by 2, this is r is equal to a, so this is a. When theta is equal to minus pi by 2, this is this is a. When theta is equal to pi, this is 0. So the value of r at this point, the value of r is 0 at this, and when theta is equal to 0 degree, r is 2a. So obviously this will go like this. Okay, so how we can find the moment of inertia about the in the question it is given that we have to find the moment of inertia about the line that is perpendicular to the initial line. So this line is the perpendicular to the initial line, this is our initial line. Okay, so we have to find the moment of inertia about this axis. Okay, about this axis we have to find the moment of inertia. Okay, so this is the plot of the chordwide of r is equal to a cos theta, r is equal to a 1 plus cos theta. Okay, so let us understand this by the concept that how a solid is being generated. Okay, so we have seen in the case of a sphere, what we have done is that we have revolved the semicircular area. Okay, so when a semicircular area is revolved about 360 degree, a sphere is generated. So this generates a sphere, this generates a sphere because we have rotated this about 360 degree. When something is rotated about 360 degree, it will generate a, so this is a semicircular area. When a semicircular area is rotated about 360 degree, it will generate a sphere. Okay, similarly in this what we will do, we will take a elemental area. Okay, elemental area at an angle of theta to the horizontal. This is an elemental area. Okay, at an angle of theta. So elemental change in theta is d theta. This is d theta. Okay, and this is r. This distance is r. So we have the change in value of r as dr. So this is dr, and this distance will be r d theta. So what will be the elemental area? dA is equal to dr into r d theta. When we rotate this about 360 degree, this will generate a ring like this. Okay, so the radius of ring will be r sin theta. The radius of ring will be r sin theta. Okay, so this will generate a ring like this. So the cross section area will be dA. So this is our cross section area. Cross section area is, this is cross section area. This is dA. dA is equal to dr into r d theta. Okay. And the radius is, this is r sin theta. Okay, so we have the elemental volume dV is equal to dA into perimeter, dA into perimeter. Okay, so we have the elemental volume as dA into perimeter. dA into perimeter. This is equal to dr into r d theta into perimeter is 2 pi of radius. The radius is r sin theta. 2 pi into r sin theta. This is dV. So what will be the dm? So dm will be rho times of dV. Okay, so this is the elemental mass of this ring. Okay, so we have studied in the case of a ring. Suppose the mass of the ring is dm. Okay, so we have the ring like this. Okay, so this is dm. So what will be the moment of inertia about its axis? I is equal to I dash, take this as I dash. So this is dm into radius square. The radius is r sin theta whole square. Okay, so this is the moment of inertia about an axis. What will be the moment of inertia about a line which is perpendicular to its axis, and that line is lying in the plane of the ring? So what will be the moment of inertia about this axis? This we have studied. This is dm into r sin theta whole square upon 2. Okay, so this is I double dash. Okay, so this we have studied like this. Okay, through perpendicular axis theorem. So this is our ring. Okay, so what will be the moment of inertia? This is mr square. Okay, so what will be the moment of inertia about a line that is passing through the center and lying in the plane of the ring? So let us take this as I, this as I, because it is symmetry. So I plus I is equal to Iz. Okay, so let us take this as Ix. This is Ix and this is Iy. So Ix plus Iy is equal to Iz. So I plus I is equal to Iz. Iz is mr square. So I is equal to mr square upon 2. So half of this will be this one. Okay, so the moment of inertia about this axis that is lying in the, that is passing through the center of this ring and lying in the plane of the ring, about this axis. So we have this as dm into r sin theta whole square upon 2. Okay, and what will be this distance? So this distance is r cos theta. What will be the moment of inertia? Value of I. So value of I will be, this is I double dash. So this is equal to I double dash plus dm into this distance r cos theta. This is r cos theta whole square. Okay, and I double dash is dm into r sin theta whole square. Okay, so let us solve this. Let us place the value of this. So we have I is equal to I double dash is dm into r sin theta whole square upon 2 plus dm into r cos theta whole square. Okay, so let us place the value here. So we have the value of dm as this one, dm into, let us place the value of So I is equal to this we can take out r square. So we have r square sin square theta upon 2 plus cos square theta into dm. So value of dm is this one, rho times of. So value of dm is rho times of dv. So we have dv as this times 2 pi, and this is r, this is r, this is r square, this is r square, and this is 2 pi r square. This is sin theta dr into d theta. This is dr into d theta, rho times of. Okay. So let us place the integration here. So this is di actually, di. Okay, so we have the integration. The value of, we have the cardioid like this. Okay, and we have taken the element like this. This is at a distance of theta, and this is d theta, and this is r. Okay, so the random value of r at any point will be, we have the equation as r is equal to a 1 plus cos theta. So at any point we have the random, the r theta is in the terms of r is equal to a 1 plus cos theta. Okay, so the r varies from 0. At this point, at pole, the value of r is 0. So r varies from 0, r is equal to 0 to a 1 plus cos theta. Okay, and the value of theta varies from 0 to pi. Okay, this is 0 to pi. Okay, so let us do the integration and solve this. So we have I is equal to, this is 0 to pi, and this is 0 to a 1 plus cos theta. Okay, so we have, let us take 2 pi rho outside. This is 2 pi rho, and we have r5, sorry, this is r4, r square and r square, this is r4, and we have this as sin square theta upon 2 plus cos square theta into sin theta, into dr into d theta. Okay, so we have r4 or dr, so this will be r5 upon 5. So this is I is equal to 2 pi rho into 0 to pi, and this is r5 upon 5. A limit is a1 plus cos theta into 0, and this is sin square theta we can place as 1 minus cos square theta upon 2 plus cos square theta. Okay, and this is sin theta into d theta. So let us place the value here. So I is equal to 2 pi rho into a5 1 plus cos theta ka power 5 upon 5. Okay, this we can write as 1 plus cos square theta upon 2 into sin theta d theta. Okay, so this we can cancel this. So we have this as, so we have the value as I is equal to pi rho a5, pi rho a5. This is pi rho a5 upon 5, pi rho a5 upon 5. This is 1 plus cos theta whole 5 into 1 plus cos square theta into sin theta d theta, Okay, so let us place the value here. So we have cos 1 plus cos theta is equal to 1 plus cos theta is equal to 2 cos square theta by 2. So let us place the value here. So this is I is equal to pi rho a5 upon 5, and this is 2 cos square theta by 2 whole 5 into 1 plus cos theta we can write as 1 plus 2 cos square theta by 2 minus 1 whole square. Okay, into sin theta is 2 sin theta by 2 cos theta by 2 into d theta. Okay, so let us further expand this. So we have the value of I as I is equal to pi rho a5 upon 5 into, this is 2 to the power 5 is 32. This is cos 10 theta by 2 into 1 plus, this is 4 cos 4 theta by 2 plus 1 minus 4 cos square theta by 2. Okay, a minus b का whole square. This times of into, this is 2, so 2 we can write as 64. Okay, this is sin theta by 2 cos theta by 2, sin theta by 2 cos theta by 2 into d theta. Okay, so this we can further simplify this. I is equal to, this we can write as I is equal to, this is 64 pi rho a5 upon 5, this is cos 10 theta by 2 into, this is 2 minus 4 cos square, this is 2 minus 4 cos square theta by 2 plus 4 cos 4 theta by 2, 4 cos 4 theta by 2 into sin theta by 2 cos theta by 2 into d theta. Okay, so let us take this as theta by 2 is equal to t. So we have this as d theta is equal to 2 times of dt. Okay, when theta is equal to, the limit was from 0 to pi. Okay, so when theta is equal to 0, t is equal to 0. When theta is equal to pi, t is equal to pi by 2. So we have I is equal to 0 से pi by 2. This is 64 pi rho a5 upon 5. This is cos 10 of t. Okay, into 2 minus 4 cos square t plus 4 cos of 4t into, this is sin t cos t into d theta is equal to d theta is equal to 2 times of dt. This is 2 times, so this we can take as 2 here, 2 times of 2 we can take out. Okay, from here 2 is also out, so I is equal to, so we can take as, this is 4 times of 4 into 64 upon 5 pi rho a5. This is 0 to pi by 2, pi by 2. This is cos of 10t. This is 1 minus 2 cos square t plus 2 cos 4t into cos t into sin t dt. Okay, so cos we can multiply this as, so I is equal to 4 into 64 upon 5 pi rho a5 into 0 to pi by 2. This is cos t and this is cos, so this can be 11. So this is cos 11t minus 2 times of cos, this is cos 11, this is 11, 12, 13, this is 13t plus 2 times of cos of, this is 11, 15t. Okay, into sin t dt. Okay, so let us take cos t is equal to u, then we have minus sin t minus of sin t dt is equal to du. Okay, so when theta is equal to 0, we have u is equal to 1, theta is equal to pi by 2, u is equal to 0. When theta is equal to pi by 2, u is equal to 0. So we have I is equal to 4 into 64 upon 5 pi rho a5. This will be 1 to 0. This is u11 minus 2 times of u13 plus 2 times of u15 into sin t dt is minus du. So this is du and we have this as minus sign. So we can remove the minus sign and reverse the limit. So this is 0 to 1. So we have the value as, let us further simplify this. So we have I is equal to 4 into 64 upon 5 pi rho a5. This is 0 to 1 and this is u11 minus 2 u13 plus 2 u15 du. So I is equal to, this is 64 into 4, 4 4 16 का 1, 256 upon 5 pi rho a5 and this is equal to u 12 upon 12 minus 2 u 14 upon 14 plus 2 u 16 upon 16. Limit is 1 comma 0. Let us further simplify this. So I is equal to 256 upon 5 pi rho a5 1 upon 12 minus 1 upon 7, which is plus 1 upon 8. Okay. So we have this as I is equal to 256 upon 5 pi rho a5. This we can further simplify as, this we can write as 1 upon 12. This we can write as 1 upon 8 minus plus minus 1 upon 7. So this we can write as 7 minus 8 upon 56 minus 1 upon 56. Okay. 4 we can take out here, 4. This is 3, 4. This is 14. Okay, so 14 minus 3 is 11. This we can further simplify as I is equal to 256 pi rho a5 upon 20 into, this is 3 into 14, this is 11. Okay, this is 2 times of 7, sorry, 7 times of 7 2 ja, so this is 2 ja 4, 128. Okay, so this we can further cancel as, this is 10, this 2 times, this is 6 and this is 4, 64 times. This we can further simplify as 5, 2, this is 32. So this we can write as 32 times of 11. 5, this is 3. So this is 352 upon, this is 21 into 5, 105 into pi rho a5. Okay, 352 upon 105 pi rho a5 is the moment of inertia. Moment of inertia of cardboard. Moment of inertia of the cardboard about a line that is perpendicular to initial line. Okay, so we have the cardboard like this. So we have to find the moment of inertia about this line. This line is perpendicular to the initial line. This is the initial line. So about this we have I is equal to 352 upon 105 pi rho a5. Okay, so this is our moment of inertia. So let us discuss question number 8. Find the moment of inertia of a disk of mass m and radius a along the tangent. Okay, so we have to find the moment of inertia of a disk of mass m and radii a along the tangent. Okay, so let us draw the disk. So we have the disk like this. Okay, so we have to find the moment of inertia about the tangent. About this line we have to find the moment of inertia. So let us take an elemental area at an angle of theta to the horizontal. Okay, so the elemental change in theta is d theta. Okay, and r change in r is dr. So this is dr, this is r d theta. So dA is dr into r d theta. Okay, this is the elemental change in d theta is the elemental change in theta. So this is our dA. dA is equal to dr into r d theta. Okay, so we have to find the moment of inertia about this axis. So distance of this elemental area from the axis, this axis is this distance. Okay, so this is a whole distance and this is r cos theta. So this will be a minus r cos theta. Okay, so what will be the moment of inertia about this axis? So we have the value of dA as this one. So let us consider rho as the density of this disk. Okay, so what will be the elemental mass? So dm is equal to rho times of dA. So this is rho times of dA is dr into r d theta. Okay, this is dm. So di is equal to, this distance is a minus r cos theta whole square into dm. dm is rho times of dr into r d theta. Okay, so let us place the limit here. So we have di is equal to, value of limit will be, theta varies from 0 to 2 pi, theta is equal to 0 to 2 pi, and r varies from 0 to a, the radius is a, r is equal to 0 to a. So on integration we get this value as I is equal to 5 ma square upon 4. This is our moment of inertia about the tangent. Okay, so this we can show through the parallel axis theorem also. I will show this. Okay, so we have used the value of rho as rho is equal to m upon pi a square. Okay, so how we can verify this with the parallel and perpendicular axis theorem? How we can show this? So we have the axis like this. Okay, so we have disk lying in the xy plane. Okay, so through this axis we have the moment of inertia of the disk is ma square upon 2. Okay, so what will be the moment of inertia about a line that is perpendicular to this axis? So this axis is, this vertical line is, this line is perpendicular to its axis. Let us take this as x and this as y. Okay, so this is z. Let us consider this as, so we have this as ix and this as iy. So from perpendicular axis theorem, ix plus iy is equal to iz is ma square upon 2. Okay, so we have this is symmetrical, so let us take this as I, this as I plus I. Let us take this as I and this as also as I, because it is symmetrical. So this is 2I is equal to ma square upon 2. So from here I is equal to ma square upon 4. Okay. So we have the moment of inertia about line that is lying in the plane of the disk, and that line is passing through the center. So about this line we have the moment of inertia as ma square upon 4, and this distance is a. Okay, so from parallel axis theorem, let us take this as I dash and this as I. So we have I dash is equal to I plus I plus mass into ma square. So this is ma square upon 4 plus ma square. This is 5 ma square upon 4. This is I dash. So about the tangent we have the moment of inertia as 5 ma square upon 4. Okay. So let us discuss question number 9. Find the moment of inertia of a rectangular parallelepiped of sides 2a, 2b and 2c passing through the center and parallel to x-axis, y-axis and z-axis. How we can solve this? Rectangular parallelepiped. Let us draw a rectangular parallelepiped. Okay, let us take the center here. Okay, so we have this as x axis, this as y axis, and this as z axis. Okay, so let us take an element here. Okay, and we have in xy plane, this is our xy plane. Okay, so we have to find the moment of inertia about Ix. Okay, so let us take an elemental mass dm. So the elemental volume dv is equal to dx into dy into dz. So we have the elemental mass is rho times of dx, dy and dz. Okay, so the length is given as 2a, 2b and 2c. So this whole length is 2a. This whole length is 2a. Similarly, whole length is 2c. And we have this length is 2b. Okay, so what will be this distance? So the distance of this elemental mass from the x-axis will be, this is distance. Okay, so this will be equal to, and we have this as this distance is z, and this as, this is z and this is y. So this will be equal to r is equal to y square plus z square under root. So the moment of inertia Ix dix is equal to r square dm. This is r square into dm integration. So this is equal to double integration r square is y square plus z square into dm is rho times of dx, dy and dz. This will be triple integration. Okay, so because this is dx, dy and dz, so x varies from, x is equal to, x varies from from this point we have varies from, this is plus a and this is minus a. The whole distance is 2a. So this is minus a to plus a. Similarly, y varies from minus b to plus b, and z varies from minus c to plus c. This is the value of Ix. Okay, so this we can change the limit from 0 to a, and we can take 2 outside. So this is Ix is equal to, similarly in 3 cases. So this is 2 into 2 into 2. This is 0 to c, 0 to b, and this is 0 to a, and this is y square plus z square into rho we can take out. This is dx, dy and dz. Okay, let us solve this. So we have the value as Ix is equal to 8 rho. So let us take the x first. So we have this as 0 to c, 0 to b. We are taking as y square plus z square into, this is dx. So x, this will directly y square plus z square into x. X limit is from a to 0. dy into dz. So this is directly a. So this we can take as limit as a. So this is dy into dz. This we can take out. So Ix is equal to 8 rho into a. This we can take as y. So this is y cube, y square dy. This is y cube upon 3. Y cube upon 3 plus z square into y. The limit is b and 0. And we have dz. The value of dz is 0 to c. Let us place the value. So Ix is equal to 8 rho a. This is 0 to c. This is b cube upon 3 plus, we are taking y. So this is z square into b. Okay, this is dz. The limit is from 0 to c. Let us further simplify this. So we have Ix is equal to 8 rho into a. We have this as b cube upon 3 into z plus b into z cube upon 3. C and 0. So we have Ix is equal to 8 rho A. This is B cube C upon 3 plus B into C cube upon 3. Okay. So we can take out BC. So Ix is equal to 8 rho ABC upon 3. This is, we can take BC outside. This is B square plus C square. Okay, so we have the density as rho is equal to mass upon volume. So rho is equal to mass upon multiplication of sides, 2A into 2B into 2C. So we have 8 rho ABC is equal to M. So this 8 rho ABC is M. So Ix is equal to M upon 3 B square plus C square. Similarly Iy is equal to M upon 3 A square plus C square. And we have Iz is equal to M upon 3. This will be B square plus, sorry, this is A square plus B square. Okay, so this is the moment of inertia of the cardioid, about of the rectangular parallelepiped, about moment of inertia of rectangular parallelepiped about x-axis, y-axis and z-axis. Okay. Okay, so we have discussed up to question number 9. So this is all about the moment of inertia. Thank you.